Hello and welcome back to the video lectures on ordinary differential equations. In the previous video, I briefly introduced the numerical solution of ordinary differential equations. In this video, we start with the first method to solve ordinary differential equations, which is Euler's method. So let us consider a first order differential equation. It's given here, and remember that we separate the terms. So on one side we want the first derivative of y with respect to x, or the first derivative of the dependent variable with respect to independent variable, and on the other side we have the function which consists of both the dependent variable and independent variable, which is y and x respectively. And in addition to this differential equation, an initial condition is also given, and this initial condition means the value of y at x0, at x equals to x0. So this initial condition means that at x equals to x0, y is equals to y0. So this is the meaning of this equation. Okay, so this is the style of writing initial condition or boundary value condition. Then to solve this differential equation using Euler's method, we use the formula of Euler's method that we saw in the previous video, which is simply yi plus 1 is equals to yi plus the slope times the step size. So we generalize this form as new value on the left side can be found out by adding to the old value of the same variable the product of slope times the step size. So m here represents slope and h represents the step size. So in Euler's method, the slope is given by this function f of xi by I, and this function is nothing but the function on the right hand side of this equation. Okay, so this function refers to the other side of this this ratio dy by dx. Okay, so let me erase this. Okay, so let us solve an example on Euler's method. In this example, we want to solve this differential equation dy by dx equals to yx square minus 1.1y. So this right hand side of this differential equation is the function f, and this function contains two variables x and y. Then along with the differential equation, the initial condition is also given, and according to this initial condition, when x is 0, the meaning of this initial condition is like this: when x is 0, y is 1. Okay, and we have been asked to find out the value of y when x equals to 2. So you can see that the value of y is initially known at x equals to 0, and we have been asked to find out the value of y when x is 2. But it's also given that we have to increase the value of x by an increment equals to the step size, which is h 0.5. We know that the formula for Euler's method is yi plus 1 equals to yi plus the function which is on the right hand side of this equation into the step size h, which is 0.5 in this example. I'm going to rewrite this formula which in the form that is more easier to understand. Okay, so this is how I'm going to write this formula: y of x plus h. So this new value of y, by incrementing the value of x by step size h, is equals to the old value of y plus the function which is on the right hand side here in the differential equation times the step size. So basically is the same formula. And to solve this example, again we are going to take the help of this tabular form. So I'm using this tabular form to make you understand the mechanics of calculation for Euler's method. Okay, so the first column of this table mentions the value of x. The second column mentions the value of y at x, which is also the first term on the right hand side of this equation. Then the second term is f of xy times h, hence f of xy is given in this column of the table. Then the step size h is given in this column of the table, but h is going to remain constant for all the iterations. And finally, in this column we have the left hand side of this equation y at x plus h. So this is the first iteration. The row 2 of this table is the first iteration of the solution. And for first iteration, we are going to start off with the initial condition, which says that at x equals to 0, value of y is known to be 1. So at x equals to 0, the value of y, so y at x equals to 0 is 1. Then f of xy, which is this function in the differential equation, yx square minus 1.1y, which we are going to evaluate at x equals to 0 and y equals to 1, which is substituted here so that you understand how we substitute the values of x and y for f of xy. Finally, the step size 0.5. So if you substitute all the values into the equation, so if you substitute all these values in the equation, you can pause the video and calculate the value of y at 0.5. Okay, so let me call this as y1. This is the value of y at the end of first iteration. Then we move on to the next iteration, as we know the y1, or as we know the value of y at x equals to 0.5. So we progress with the next value of y. Now using this new value of y, which is known at x equals to 0.5, we compute the value of y at x equals to 1. So we increment the value of x by 0.5. Okay. So this is the second iteration. So this was first iteration, and now the second iteration is already there in this table. In the second iteration, the value of x is 0.5, and the first term on the right hand side is y at 0.5. Then the function f of xy is calculated at x equals to 0.5 and the new value of y1. So we have already incremented the value of x by 0.5, and the y is the new value of y that we obtained at the end of first iteration, which I have already written as y1. So we substitute those values into the right hand side of this differential equation, and we calculate this value of function f of xy. The step size is as it is 0.5, and finally calculate the value of y at x equals to 1, and I will call this as y2, which is the value of y at the end of second iteration. Okay, so we proceed in this way, and finally we obtain the value, or we obtain subsequent values of y, which are y3, y4, and y4 is the value of y at x equals to 2, which will appear here in the last iteration. We stop our computations here. So I'm not gradually doing the calculations in this video. What I expect is that you pause the video and try to calculate the whole thing yourself, because it doesn't matter how much I solve. This mechanics of calculation you should get by yourself, because this is a little tricky. Okay, so it looks trivial from the outside, but when you start computing on your own, you will realize that there is some complexity involved while substituting the values. Okay, so finally I would like to give the solution to this example, and I have mentioned the values for each iteration of the solution. You just pause the video and calculate all of those values and verify uh, your solution. Okay, so finally the value of y at x equals to 2 comes out to be 0.38715 here at the end of the fourth iteration. Okay, so this is the Euler's method. The formula for Euler's method is simple, but the mechanics of calculation is difficult. Okay, so I insist you to stop the video here itself and don't end this video until you solve the example. Okay, so in the next video I will start with the improvements in Euler's method. See you in the next video.